Okay, I'm going to talk about what is the spherical coordinate system. And this is, I would say, the by far the most useful type of coordinates you'll see, but much more than cylindrical coordinates. Um, it shows up in a lot of places. For example, you'll see it if you take any quantum mechanics course, like if you take physical chemistry, if you take physics. You also see it in mechanics. Because reality is just three-dimensional, and the reality is, in general, when you get to very large distances, everything sort of looks like a sphere, in some sense. So spherical coordinates is a really nice. It's a nice simplifying representation of physical space. You also see it in electromagnetism, and there's basically a lot of integrals you'll use, which describe both electric and magnetic fields, and all of them use spherical coordinates. And you can then compute physically observable quantities, which if you take a good E&M course, you'll have a laboratory experiment to corroborate a lot of this stuff. So I would say this is it's a very useful idea. Although it's a little opaque, so I'll try to simplify it. So what are they? They are coordinates where you have rho, theta, and phi, and this theta here is the polar coordinate that you're all familiar with. And this thing now is the 3D radius, and this thing is an extra angle. And this is called the polar angle. And let me just briefly digress and say, why is this called polar? Why is phi the polar, and why is theta not the polar? Well, we have to ask, why is theta called the polar coordinate system? So if you have xy, we all know that this angle here is theta, and we are in polar coordinates. Well, that's because this point, the origin, is called the pole. And in fact, the z-axis, where that point is located, this z-axis is called the polar axis of the coordinate system. And all of this polar is motivated by the Earth itself, because we have the North Pole and the South Poles. And you can think of the z-axis as connecting those two poles. And so the polar coordinates would then describe the equator. You could think of it then as the equator. And now spherical coordinates will now describe the full real Earth. Okay, so hopefully that doesn't confuse you as to why we're adding phi and calling that the polar angle. So what is the system, and how is it related to x, y, z? Relation to the x, y, z Cartesian rectangular coordinates. So if you call polar, this was xy equals r cosine theta sine theta, because we were using the unit circle. If this is yx, and we drew a triangle with angle theta with radius r, then we knew that y is r sine theta, and x is r cosine theta. Okay, so it follows from that picture. So now what you do in spherical, it's really like two polar systems. And then, so you need two diagrams to think about it. So the xy diagram is okay. It'll be the same as before. So here's y, here's x, theta, r, and from here you can get x equals r cosine theta, y equals r sine theta, just as before. But now what we're also going to do is we're going to draw an RZ diagram. So we'll again draw our line, and Z will be at the top now. So Z against like the Z-axis. R will represent the plane contribution. And instead of below the line, we'll put phi above the line. So phi will be measured from the polar axis. That's why we do that. Measured from the polar axis. And remember, that's why we're calling it the polar angle. If we measured from the equator, that would actually be called the elevated angle, but you don't need to know that. We're just going to stick with the polar angle measured from the z-axis. So here's phi, and again, we had r, so now we need a radius rho. Rho will then be the square root of r squared plus z squared. It's also just x squared plus y squared plus z squared. Okay? And once you have this triangle, you can then deduce that this z is equal to rho cosine phi, and this r is equal to rho sine phi. So we can write, let me just write the equations. They're x equals r cosine theta, y equals r sine theta. That's for the xy diagram. And now for the z diagram, we'll have r equals rho sine phi, and z equals rho cosine phi. And again, the reason we have sine and cosine switched is just because we're measuring phi from the pole and not from the equator. So I know that can be a little confusing at the beginning, but these will define spherical coordinates for us. I think this is a more compact way than a lot of books will present this, but let me just relate this now to what you'll more often see. Spherical coordinates will then look like this. X equals r cosine theta. Well, now if you use the RZ plane, this becomes rho, let's see, it's rho sine phi times cosine theta, and y will look similar. It's r sine theta as before. And now if we go back to the RZ plane and relate this to the 3D radius, it's rho sine phi times sine theta. And we go back to z, and we have again rho cosine phi. So now this is the more common spherical coordinate representation. And I would also call it more messy. It's harder for me to look at least. So if you want a more compact way, you could so the way I showed you was just look at x, y, and RZ diagrams, and this will help keep it all straight for you. Just remember that phi is the polar angle. This is what we did previously. So, but there's a second nice compact way, and so I would just think of this as nested circles. Nested circles, but what I mean here is really what's going on is x, y, and RZ, we're using two different unit circles. Not unit circles, but we're using two different circles. So two circles. So the first circle is r cosine theta, r sine theta. The second circle is rho sine phi. Remember, this is x, y. And now we're going to do RZ. So rho sine phi, sine phi and rho cosine phi. I'm just going to put the diagrams here just for clarity's sake. Z, R, phi, rho. And so what I would suggest as another way is you can replace x, y, z with something like r cosine theta sine theta, and then we have z here. So this uses the first circle. And for the second circle, you could write something like this: rho sine phi, and then factor that out of the first circle, and then rho cosine phi. So this is another way of writing x, y, z. So you can think of it as a circle within a circle, right? Because you know that the outside contributions, they have a circle, right? So rho sine phi squared plus rho cosine phi squared, this is equal to rho squared, of course. And we also know that the inside has something similar going on. So cosine squared theta plus sine squared theta equals 1, right? So you can think of this as the red thing as a circle parametrizing a circle. And visually what this means is that if you go back to the RZ diagram, you can sort of imagine there are circles emanating as you vary theta. As you rotate the RZ plane with your theta angle, that adds circles to this first circle. So hopefully that wasn't too confusing. But what I'm just trying to say is you don't have to just write it out in this long kind of sine, cosine, sine, sine representation. There are other more, I would say, suggestive ways to think about this. And it's also worth, if you're ever confused about whether it's sine and cosine, so why is it cosine phi and not sine phi for z, I mean. Remember, z was rho cosine phi, as from this diagram here. From the RZ diagram. Well, I think it's just, remember, just plug in phi equals 0. And this will give you the z-axis. And then you'll get z equals rho. And so on our diagram, that is exactly what we would hope. See, because now z and rho, they match up exactly. Z equals rho. And so that's why we use cosine, because cosine is 0 is 1. If we had sine there, we would get 0, but z is not 0, r is 0. So that means r is the sine. 1. Okay, and then it's also, if phi is the polar angle, what do we call theta? Okay, theta is called the azimuthal angle. And I know it's all confusing, because you would think that because theta is from polar coordinates, we call it the polar angle. But again, think about the axis, and think about the axis and the spheres and the north and south poles. Okay, that's all for this video. Thanks for watching.